In this video, we're going to begin our discussion of wave motion, and specifically here we'll be looking at the basic properties of waves. So the first thing we have to talk about is, what is a wave? Well, a wave is a vibration that moves through space. I want to take a minute here to kind of help you understand what a weird concept this really is. Let's say that we've got a couple people here, and they want to play catch. So this person starts with a ball, throws the ball to our other person. And so in this case, a physical object goes from person 1 to person 2. And of course, that's the kind of problem that we do a lot in first semester physics. But now let's think about what we're talking about now. If instead of throwing a ball, what this person does is they simply speak, what's happening there is the vocal cords in person 1 are vibrating. That's creating a sound wave. And then that sound wave or vibration travels through the air to this person's eardrum that allows them to hear it. Notice that no material object went from position 1 to position 2. In fact, all that happened was each little air molecule did its part to pass the vibration to the next air molecule. So this air molecule didn't really move other than just kind of going back and forth and pushing the one next to it, which then moved back and forth and pushed the one next to it. So no material object went from person 1 to person 2. Only the movement moved. So that's what wave motion is. It's a vibration or movement that moves through space. A very different kind of concept than what we saw in first semester physics. Now, how do we create a wave? Well, I already alluded to it there with the vocal cords. A wave is created by something that oscillates or vibrates. So for example, if we take a tuning fork and we hit it on something, that tuning fork will begin to vibrate, and the tines of the tuning fork will actually vibrate back and forth in simple harmonic motion. Now, hopefully you remember a little bit about simple harmonic motion from your first physics course. Just to remind you a little bit about it, let's take a look at the following slide. So here I've kind of reviewed the important stuff about simple harmonic motion. Remember that if we have a mass on a spring, whether we have it horizontally without friction, or whether it's moving vertically, that object will oscillate with simple harmonic motion. And so what that means is if I displace my mass an initial amount a, which is the amplitude, that object is going to oscillate between a and negative a, and the position as a function of time is given by a cosine omega t. Remember that omega in this situation is simply 2 pi over the period, where the period is the time for one complete motion. So in other words, this would be a time of one period. The velocity as a function of time, remember, is just the derivative of position versus time. So we get negative omega a sine omega t. And again, the acceleration is the second derivative of position versus time. When we talked about this in our last class, what we determined was that the period is equal to 2 pi times the square root of m over k. Remember here, m is just the mass of the object, and k is the spring constant. So if we've got an object that's oscillating with simple harmonic motion, then it can create a wave. Now, any vibration can create a wave, but we're really going to be looking specifically at waves created by objects that are oscillating with simple harmonic motion. I want you to kind of pay attention to this formula, because in our next video, when we get to the equation for a wave, you'll see that it has a lot of similarity to the equation for something that's vibrating in simple harmonic motion. Let's take a look at some information about sound waves. In this course, we're primarily going to be interested in light waves or electromagnetic waves, but we'll say a few things about sound. One of the things that's interesting about sound is it requires a medium. A sound wave has to travel through something. Therefore, if you're up in space, in the vacuum of space, there is no sound. So when you're watching, a Star Wars film and you hear a big explosion when the Death Star blows up or something, in reality, you wouldn't hear anything. There's no medium, there's no air, and therefore sound can't travel in a vacuum. Sound can travel really through any material, air, water, metal, etc., but it does require something. It requires a medium to travel in. The speed of sound in air at room temperature, standard temperature and pressure, is about 343 meters per second. The speed of sound does change with air pressure and temperature, so that's an approximate value in most circumstances. Let's talk about light waves. Now, in general, in this course, when I'm talking about light waves, I'm using the term more generally than just visible light. What we're actually talking about are what we call electromagnetic waves. Electromagnetic waves are made up of oscillating electric and magnetic fields, and visible light is an example of an electromagnetic wave. But it turns out there are others: radio waves, microwaves, like in your microwave oven, infrared, ultraviolet, X-rays, and gamma rays. Those are all just different types of electromagnetic waves, and in a later video we'll get into the details of all of that. So for electromagnetic waves, no medium is required. We know that light will travel through a vacuum because if it didn't, we wouldn't be able to see the sun. All electromagnetic waves travel at a speed of 3 × 10⁸ meters per second in a vacuum. When a light wave goes into a material like water or glass, then it will travel slower. But in a vacuum, the speed is the same for all types of electromagnetic radiation. Notice, by the way, that the speed of light is roughly 1,000,000 times more than the speed of sound. And that's something that I'm sure you've noticed many times. If you're at like an outdoor concert, you'll notice that if you're pretty far back, you see the drummer hit the drum, and then, a fraction of a second later, you actually hear that drum beat. Another great example is thunder and lightning. You see the lightning, and then a few seconds may go by before you hear the thunder. And that's simply showing you the difference between the speed of sound and the speed of light. Let's talk about the types of waves. There are actually two types, transverse and longitudinal. Let's start out by talking about what is a transverse wave. On the slide, I tell you the direction of the wave travels. The direction the wave travels is perpendicular to the direction of the vibrating source. Here's what I mean by that. Imagine that if we were in class together, I would take a long slinky and stretch it out across the classroom. And to demonstrate a transverse wave, what I would do is I would take my hand, so this is a top view of the slinky on the ground, and to create a transverse wave, I would shake my hand back and forth in this direction. What I would see then is the wave would travel in that direction. So you'll notice that the direction of the vibrating source is perpendicular to the direction that the wave travels. And so what we would see is we would see each of these crests and troughs traveling to the right down the slinky. By the way, electromagnetic waves are transverse waves. The other type of wave that we have are longitudinal waves. And in this case, the wave moves along the direction of the source vibration. So again, imagine we've stretched a big slinky across the floor, and this time I take my hand, and instead of moving it back and forth, I move it forward and backward. And what I'm doing then is creating compressions and expansions in the slinky. And again, those would travel in this direction. So in this case, the vibration that creates the wave is along the same direction back and forth as the direction the wave will travel. An example of a longitudinal wave is a sound wave. A sound wave is a pressure wave, meaning that the air molecules are pushed together or pulled apart as the wave goes by, and it really effectively would look just like this. We'd have areas where the air pressure is dense, where it's less dense, dense again, etc. Now that we know the two types of waves, transverse and longitudinal, let's look at what the properties are of waves. How do we characterize one wave or differentiate one wave from another wave? Well, the first important property is the property of wavelength. The wavelength is the distance between crests or troughs of a wave. We use the Greek letter lambda to represent wavelength. And so in this picture, the wavelength would be this distance. So it's really the distance over which the wave repeats itself. So in other words, I could really pick any two identical points on the wave. In other words, that would be the wavelength. I could pick the distance between troughs. That would also be the wavelength. So think of it as the repeat distance of the wave. How much distance goes by before the wave gets back to the same position? In a longitudinal wave, same idea. We could measure, for example, between the maximum compression and the next maximum compression. That would be the wavelength. But we could also measure between the maximum expansion and the next maximum expansion. Okay, so that would be the wavelength for a longitudinal wave. The next important property of a wave is the frequency. So we know what frequency means from simple harmonic motion. It's just the number of oscillations per time. And we use the unit of hertz, meaning cycles per second, for that. In this case, though, what we're referring to is the frequency of the vibration that created the wave. So for example, if I'm shaking my hand back and forth with a frequency of 3 times per second, then the frequency of the wave is 3 hertz. Once the wave is created, the frequency doesn't change. Okay, so the frequency is determined by the vibration that creates the wave. And that's no different if we're talking about a longitudinal wave and the frequency I'm moving my hand in this direction. Let's talk about the amplitude of a wave. This is our third important property of a wave. The amplitude is the distance from the midpoint to the crest or the trough. Now, you'll notice that the amplitude of the wave is exactly the same as the amplitude of the vibration that created it. Notice it's the same A as in simple harmonic motion. So if we're creating this wave that's traveling down the slinky, our wave is traveling in this direction, and the maximum displacement from the midpoint is simply the amplitude A. Now, one of the things that's a little bit confusing about seeing wave motion versus simple harmonic motion is what I'm picturing here is y versus x. In other words, this is a snapshot. And by a snapshot, I mean what the wave looks like at one particular time. When we saw graphs in simple harmonic motion, so you can probably picture, as we just reviewed a few slides ago, position versus time for simple harmonic motion. Notice that again, that's the amplitude, A and negative A. But what we're plotting there is x versus t. The mass is simply oscillating up and down, and we're plotting its position over time. Here, this is what the wave actually looks like at a particular time. If we looked at the wave a short amount of time later, it would have simply moved over to the right. Okay, so that's what amplitude means. Amplitude for a longitudinal wave, again, is just how much the wave is compressed or stretched relative to its equilibrium position. It's a little bit harder to represent that with a drawing. So, how do these properties of waves affect the way we perceive the waves? Well, let's look at frequency first. For frequency, the frequency of a sound wave is what we interpret as pitch. So a higher frequency sound wave has a higher pitch to us. So in other words, a bass guitar is a low frequency. A regular guitar would be a higher frequency. As you're playing notes on a piano, when you're down at the way left end of the piano keyboard, those are low frequency notes versus all the way to the right, those are high frequency notes. For visible light, the way we perceive frequency is color. So that would be for visible light. Overall, for the entire electromagnetic spectrum, including radio waves, microwaves, gamma, X-ray, etc., what the frequency determines is the type of electromagnetic wave. So for example, it turns out really the only thing that makes a radio wave different than visible light is it's in a different frequency part of the spectrum. And we'll be getting into that in much more detail in a later video. The other wave property that we perceive is amplitude. So for sound, amplitude has to do with how loud the sound is. A bigger wave amplitude we're going to perceive as a louder sound. Now it turns out it's not a linear perception. For those of you who have heard of the decibel scale, that's why we have this decibel scale, because it turns out if you make the amplitude 10 times bigger, we humans only perceive that that sound as being twice as loud. And so the decibel scale is a logarithmic scale just because that's how we humans perceive amplitude. For light, it has to do with how bright the light is. So the brightness is what we perceive as the amplitude. Notice, by the way, we don't perceive the wavelength. And that kind of makes sense because ultimately, if you think about it, when a sound wave reaches your eardrum, ultimately what it's doing is it's making your eardrum vibrate with the same frequency of the sound wave. So that's what's important, is how it's vibrating your eardrum and how much it's vibrating your eardrum. So those are the frequency and the amplitude. Let's talk about the velocity of a wave. It turns out that the velocity or speed of a wave is equal to the frequency times the wavelength. Now, the first thing we might want to do here is just check our units and make sure that that makes sense. We know the units of hertz, or the units of frequency are hertz. The units of wavelength would be meters. But remember, hertz just means anything per second. So that's really just 1 over seconds times meters. And we can see that that gives us the correct units for velocity of meters per second. But let's talk about where this formula comes from. It really comes from that very basic concept that velocity, or average velocity, is delta x over delta t, way back from physics 1. So now what we want to think about is how far does the wave go in one period. So if I take my hand and I go up, down, and come back, so I've moved my hand through one period of time, how far does the wave go? Well, the part of the wave that was here as I started has now made it all the way to here in one period. And so you'll notice that a wave travels one wavelength in one period. Well, of course, we know that frequency and period are inversely related, and therefore the velocity of the wave is the frequency times the wavelength. So that's where that formula comes from. It just comes from the concept that a wave will travel one wavelength in a time of one period. Now, it turns out that the velocity of a wave depends on properties of the medium. So, for example, we've already talked about the fact that a sound wave, the speed depends on the properties of the air that the wave is traveling through. So, for example, the air pressure and the air temperature. Another example is the speed of a wave on a string. And we're going to really concentrate for the rest of this chapter mostly looking at waves on strings. So imagine I've got a string and I shake my hand and I can create a wave traveling down the string. The string is anchored, let's say, against at the wall on the right. It turns out that the velocity of the wave on the string will depend on two important properties. How tight the string is, so in other words, the tension in the string, and we're going to use F subscript T for tension. Notice we're not using capital T because we need that for period. It's also going to depend on the thickness of the string. And the quantity that we use to represent that is mu. And what mu stands for is mass per length. So mu has units of kilograms per meter. Notice, as I point out here, has nothing to do with the coefficient of friction, which is what we used mu for in Physics 1. Okay, completely different use of the letter mu. So if I want to figure out what is the mass per unit length of a string, literally I just take a certain length, measure its mass, divide by the length, and that's the mass per unit length. You'll notice that the thicker the string, the slower the velocity. The greater the tension, the higher the velocity. Again, not linear because we've got the square root. But if I increase the tension, the velocity of the wave is going to go up. So here's a question. If I change the frequency, does the wavelength, the velocity, or both change? So again, pretend I'm creating this wave traveling down a string. Again, just by taking my hand and shaking it back and forth. You'll notice this would be a transverse wave. Wave is traveling this way. The vibration is going back and forth in this direction. So if I change the frequency that I'm shaking the string with, does the wavelength, the velocity, or both change? Well, we've got this formula that v is equal to lambda times f. And so if I change f, you'll notice that just looking at this formula, I can't really tell, because if f changes, v could change, lambda could change, or both. But here we have to remember the key thing we just learned, which is that the speed of a wave depends on the properties of the medium. In other words, for a wave on a string, v is equal to the tension divided by the mass per unit length divided by the square root. So if I don't change the tension or the mass per unit length, then v is constant. Okay? So v is constant unless I change properties of the medium. And so in this question then, if all I'm doing is changing the frequency, I haven't changed the tension in the string, and I haven't changed the mass per unit length of the string, which I'd have to do by actually just getting a different string, then v has to be constant. And so therefore the answer to this question would be only lambda changes. So that's important, that in general with this formula, unless the medium is changing, v is constant. So if f goes up, then lambda has to go down, and vice versa. Why don't you go ahead and pause the video and just do this one example problem. Okay, let's go through this together. It says the lowest string on an electric guitar has a mass per unit length of 0.00570 grams per centimeter. What's the mass per unit length in kilograms per meter? So first part of this question, just a quick unit conversion review. Remember, the way that I like to see unit conversions is I want to see the thing you're converting, what the units are of that, and then I want to see your conversions. So we know that in 1 kilogram there are 1,000 grams. So grams is going to cancel with grams. We know that there are 100 centimeters in 1 meter, and therefore centimeters and centimeters will cancel. And now I just have to multiply across the top and divide by the bottom. And we can see that what we end up with is 0.000570 kilograms per meter. Now, we want to make sure to always pay attention to the fact that if we want our velocity to be in meters per second, mu has to be in units of kilograms per meter. So if you get it in grams per centimeter, make sure you remember to convert first. If mu is in kilograms per meter and force is in newtons, then velocity will be in meters per second. Second part of the question, the string is tightened to a tension of 77 newtons. what is the velocity of the wave on the string? So now we can just plug in the values. We have ft over mu. So that's the square root of 77 newtons divided by 0.000570. We can see that for both numbers we've got 3 sig figs, so our answer should have 3 sig figs, and it's 368 meters per second. And by the way, those are realistic numbers. That is the speed of a wave on a guitar string. Okay, so that's going to end this video. In our next video, we're going to look specifically at what is the equation that describes a wave traveling down a string, or any traveling wave. And then we're also going to introduce a new concept, which is the concept of a standing wave.